Hello, viewers, and welcome to day 3 of Advent of Code in Rust. As you may know, if you've been following along, I created a YouTube channel the other day and have been doing Advent of Code 2019 in Rust. We have day 1 and day 2 videos are out, and right now it is day 3. And all the code that we have been writing is in this repository under my name, BC Myers, and AOC 2019. And you can find where we left off, or where we are, here. So with that, we're going to tackle the day 3 problem. And it's more interesting than day 1 and day 2. And there's quite a lot to talk about and quite a lot to do. And so let's get started. I have a tmux session, as always, called AOC, which has our shell and panes all set up. And like the other day, I created a to-do list to remind me what it is that I want to cover. So we're going to do a couple things today. We're going to make a small change to all of our run functions to make testing easier. That'll be quick and easy, and you'll self-explanatory once I get into it. And then I thought it'd be interesting, again, with the going on the theme of I'm sort of more interested in the infrastructure and setting up a robust project than I am actually solving the Advent of Code problems. I want to sort of teach you about Rust, and this project, solving these codes, is just a sort of solving these Advent of Code problems is just that just happens to be the things we're working on. But I want to over-engineer the solution a little bit to sort of show you interesting aspects of Rust. And one interesting aspect that we can cover today, because it'll be relevant, is benchmarking, as well as logging. So let's add that sort of infrastructure to our code and then solve day 3. Now I'm going to solve day 3 actually in a relatively simple way that is not the way I solved it in the beginning. But after I solved it, I went online and looked at what other people did, and this seems to be the most straightforward way to do it. And it's easy for me to code, well, it's not easy for me to code it live, but it's relatively easier for me to code it live than the original solution I had. So we're going to do that. But then I've already prepared a sort of faster, messier version, which represents my first attempt. And that's already coded, and I will sort of walk through that code with you because I don't trust myself to be able to cleanly rewrite it on stream without making too many mistakes and getting lost. So that's the plan for the day. Talk about benchmarking and logging, do day 3 in a way that will run in milliseconds. In fact, I have sort of already benchmarked the simple version that I'm going to code for you of day 3, and it looks like it's taking around 59 milliseconds to run. But this version, the faster version, takes microseconds. So it'll be cool to see that. And once we have benchmarking in place, we can sort of make these pretty charts that show us about how much time we run. So let's get into it. So the first thing I wanted to do is make a small change to our run functions. Basically, I don't like this. I don't like run2 and needing that for the testing infrastructure. So let's just have all our run functions return a tuple of our answers for part 1 and part 2. And these will need to be strings because I want all the functions to return the same value, and then in our actual main.rs file, we'll just print the strings to standard output. So instead of printing them here, let's just return answer 1 and answer 2 as strings. So let's see, format answer 1 and format answer 2. Okay. And so that way we can actually use this as our run function, and we don't need run2 anymore. So let's move this up here, do away with that. Oh, I guess I should have kept the formatting, but we'll do format, turn these numbers into strings, format I guess we could return a box of something that implements display. That might be something to think about. But let's get this done, and then we'll figure that out later. We cannot borrow input as mutable, because now this has to be mutable. And our tests will no longer work here. So expected, these need to be strings now. Or static slices of strings. I'm not terribly versed in Vim. I know there are ways to do this a lot faster than I'm doing it, but you guys have to bear with me as I learn learn Vim. So there we go. That should just work, because now we're comparing the output of run, which is a tuple of strings, to our test cases, which are strings. So our code will not compile yet, because what we need to do in main is take care of the fact that all of these are now going to return strings. So what I want to do is match on the day and say let answer 1 and answer 2 equals the result of that. And then at the end we will print out answer 1 and answer 2. So all the printing happens here in our main function. So let's go change the signature. We changed the signature for day 1. Let's change the signature for day 2. So we want to return 2 strings. And let's see. This is answer 1. And this is answer 2. Answer 2. And what we want to return is format of answer 1, answer 1, and format of answer 2, which at the moment is a result, so let's unwrap it. And I think that'll just work, because we're not testing the output of execute here. We're not testing the output of our run function. So, and by the way, I think this returns a result. I noticed that yesterday. Okay, so that's all done and dusted. Now let's do day 3. Just say string, string. And now the signature of our run function should be consistent, and we should be able to compile. And let's run day 1. Let's run day 2. Oops. And day 3 will not work, but let's run our tests. And they all still pass. And so that's a nice little change. Should we just go ahead and commit this? I guess. Git status. Notice we have this untracked file of day 3 version 2. That's the answer that I already coded up and I'm going to show you. So we'll keep that untracked in our Git file. And I changed git ignore because I moved our to-do into a local folder. So now git ignore is just ignoring everything that we put in the local folder, because if we go into local, we have our to-do, and we also have this benchmark image, which I wanted to show you. But now that we have this local folder that's not tracked by Git, we can just throw stuff in there, and we don't have to worry about it getting put up on GitHub. So let's see, git status. Let us git add, git ignore, git add source day. Can I do this with Git? Oh, I can. And git add source main, and we'll do git status, And these are the changes to be committed. Oh, I don't want a new file. Oh well, we'll put the new file up there anyway. Git status, git add all, git commit im, small change to run functions, and day 3 version 2. Let's see if that worked. Yep, small change to run functions and day 3 version 2. So here, by the way, is the solution, the fast solution. We'll go over that. I didn't want to commit that just now, but oh well. Okay, so let's go back to our to-do list. And this is complete. So let's add the benchmarking infrastructure. So in Rust, I think the standard for benchmarking is this wonderful crate called Criterion. There's the ability to benchmark if you use nightly on Rust just with the standard library, but Criterion basically gives you all of the good stuff that you can use on stable. And so we want to pull this in, but actually you don't pull it into your crate like we have done before. There is a user's guide that I want to copy and paste from. Or here, quick start. This is what I wanted. So the way to pull in Criterion and do proper benchmarks in Rust is to go to your cargo.toml file and add this. And for every benchmark file you have, you need to add one of these list elements. In TOML, this means that we have a list. This is an element of the list bench. Anyway, let's call it benchmark. And for various complicated reasons that I don't want to get into, you got to do this harness equals false thing. So good. Now we have Criterion in our cargo.toml, and let us create a directory called benches. Is I think what you have to name it. Yep, benches. And touch benches, we're going to call our file benchmarks.rs. Is that what I named it? Let's see, cargo.toml benchmarks.rs. Okay. Now let's open up benchmarks.rs, and we'll paste in some of the boilerplate from Criterion. Boom. All right, we're not benchmarking a Fibonacci function, but we are benchmarking our library. So let's bring in AOC 2019. And we're not going to need black box. And let's see. So we want to benchmark day 01. That's what we'll call this benchmark. And we want it to run in a loop. So the thing we actually want to benchmark, you put in here. We want it to benchmark AOC 2019 day 1 run on a reader dot unbound. Good. And we have an incorrect closed delimiter. We don't need you. Okay. Good. So now we're going to run in many times and get many samples for this function here. But we need to give it a reader, and I don't want the reading of the file to be benchmarked, and so let's read in the file out here. Excuse me. So we want to read in as a buff reader, or we want as a buff reader. Well, first of all, we want let's get as a string our input data. So fs read to string, and we give it a path, and the path we want for this one is data01.txt. This can fail, so we unwrap. that gives us a string of the day 1 data, and let us just all in one line wrap that in a IO buff reader new. So we need to pull in use standard FS and use standard IO. Oh, and you can't do that. Sorry. So what we want to do, we want to get the string, and the reader will be IO buff reader new on the string as bytes. Which we need to do every time because we need a new reader. So that is how we do this. I'm remembering. Day 01 as bytes. There we go. Okay. So what we're doing is we're reading in the input data as a string, and then every time we do a benchmark, which is going to run many, many times, we just wrap that string in a reader and pass it to our run function. So that is day 1 sort of all done and dusted. Now let's benchmark day 2. And day 2 is going to read data o2.text. We want it to we want to call this benchmark day 2, and we are going to run day 2 on day 2. Okay. I'm fairly certain now that this will just work. Let's try it. Cargo bench. We're going to have to go through a bunch of compiling. Apologies for the cough, by the way. Oh, I need to take a drink of water, but, well, I have coffee by me, so I'll take a drink of coffee. Alright, so as you can see, we're running our benchmarks. Day 1 is warming up for 3 seconds. Now it's collecting 100 samples. It's going to take about 5 seconds. And there we go. Our code is running in 10 microseconds. And now we are going to, we warmed up for day 2. We're going to probably take about 20 seconds to run this benchmark. These benchmarks, by the way, I think are all going to run slower than when I ran them before because obviously I'm doing OBS. Although all of our code is single-threaded, so I don't know if that's actually going to be an issue. But it looks like it takes about 3 milliseconds to complete that. And what's neat about Criterion is if you have GNU plot on your system, which if you're running Arch Linux like me, you can install just like that. Then Criterion has created for us nice, pretty pictures that we can open with Firefox. So let's open. How do I open a file in Firefox? I think I have to do menu bar, file, open file. So if we look in my target directory, which again I've set using the cargo target dir environment variable especially to be in my home folder. Usually the target directory will be in your projects folder. But mine is here. As part of the, in addition to our debug and release build artifacts and our binaries and everything, we get this Criterion folder with a report folder that has an HTML document in it. And as you can see, so because I've run this before, we have day 3 still in there and another day 3, but you'll just have day 1 and day 2. And this was the result of our benchmark. So if we go to the command line, we can see on average it took us 10.6 microseconds to do day 1. But this gives you like a very nice plot of, well, it's the distribution of all of the samples that it collected. And some really handy information. So this is sort of great benchmarking software in my opinion. Let's take a look at day 2. So day 2 had looks like a more normal or less skewed distribution, and on average took 3 point something milliseconds. So that is sort of an introduction to Criterion, and it's a wonderful way to just throw in quick benchmarks to your project. Oh gosh. One quick note on these sort of macros here. I really don't like the macro magic that Criterion uses. There's all kinds of things to like dig into in this library about how it works. But one thing I did want to point out is that we're running our benchmarks with all of the default options. If you want to run it, if you want to sort of tweak those options, let's see. Let's go to crates.io and see the documentation. I think if we go to the documentation for these macros, you can see there's a way to make Criterion groups where you give it a config. So we won't really change the default options, but let's just do that to show you a different syntax that you can use if you want to add more information. So I guess I have to explain this a little bit. So this right here, this function that we created, is, I think in Criterion's parlance, a target. So our target here, you can have multiple targets, as you can see with this macro. We only have one. Let's call our target 01 in case we want to add more. In fact, let's create a second target so we can give different options to the different days. So we have target 1 and target 2. We're going to pull day 2 out into its own target. So target 02. This function needs to take a mutable reference to a Criterion object. And let's stick that in there. Oops. Oh man, guys, I can feel myself about ready to cough again. I think I'm getting sick. Oh, this is terrible. Terrible way to stream. And this one, let's call it target 01. So now we have our 2 targets that are going to be in this group, and we can name our group whatever we want. We only have one, so let's just name it group. And in the Criterion main, you give it one or more groups. So if we had, group 2, group 3 here, we could give it more than one, but we only have one. So that's kind of how these macros work. I'm not a big fan because although once you learn how to use them, they're pretty intuitive. It is sort of like it requires you to learn a whole new language that has nothing to do with Rust just to use this library, which is kind of a pain. But as you can see, now that we've done this, we can modify our Criterion object, which has a lot of options on it. So let's go to the Criterion object in the documents. And as you can see, we can say, we can change the measurement, the profiler, the sample size, the warm-up time, the measurement time, the default number of resamples. I mean, all kinds of interesting configuration. So let's just change the warm-up time, which I think by default is 3 seconds. So let's say warm up time, and this takes a duration. Let's say we want it to warm up for 5 seconds instead of 3 seconds. And I think here we need to call finish. Or is that not true? No, this just passes a Criterion, so we're good here. We can just... Okay. So obviously we need standard time duration. And so now we've changed our benchmarks to run. We put them in 2 different groups, and they're going to run with a warm-up time of 5 seconds. So let's test that. Cargo bench. While I try and get rid of this cough by drinking some more. As you can see, we're warming up for 5 seconds now. So I'll leave it to you to sort of go over and see all the different options you can tweak with Criterion. It's a very robust library. But to get the sort of basics of benchmarks up and running, this is what I would recommend you do in Rust. Use the Criterion library. It's fantastic, even if you have to mess with macros that are funny. Once you run a benchmark once, you can see that it keeps track of what your last benchmark was, and we apparently have regressed by 6%. And here, we've improved actually by a little bit, but it's not statistically significant. So that's why this is not colored. whereas this one right here is red because apparently that is a statistically significant change. And by the way, this is also something you can change in your criterion config, but I think statistically significant here means p-value of 0.05 or below. Oh yeah, here we go, p-value of 0.05 or below. So we have, it's either a 90% confidence interval or 95% confidence interval, depending on if they're doing one or two-sided tests, I forget. But this is not a course about statistics. This is about criterion and getting these pretty charts. Okay, so that's good. Let's put in, we won't run our benchmarks again, but let's just get ready for day 3. So if we have day 3, day 3, I should probably create a way to not have to type all this stuff manually. Day 3, and we want to run day 3, and we'll add target 3. Okay, so now this should fail, or wait, yeah, I should panic because our run function for day 3 panics. But well, I won't run it. Anyway, hopefully that's set up for what we need to do when we actually have day 3 in place. So that is benchmarking all done and dusted. So add logging infrastructure. We actually don't have to do this anymore. The reason why I wanted to add logging is because in our code we were sort of hard coding the run functions, printing out the standard out. And so when you run the benchmarks were printing out the standard out all the time, which obviously, well, A, it fills up your terminal with a bunch of junk, and so you have to scroll around to see the results of the benchmarks. But B, I don't think we need to be benchmarking how long it takes us to print the standard out, which has nothing to do with our sort of algorithm. And so what I did before was I changed all of our print lines into using a logging library. That way we could sort of turn them off in our benchmarks, but keep them on when we run our main functions. And it was a way to avoid getting around or avoid printing stuff out when we were benchmarking things. We might do this later because it'd be nice to show you logging, but since it doesn't really have that much to do with day 3 or advent of code, let's just go straight into day 3. All right, so day 3 is more involved than days 1 and 2 were. Let's go check it out. All right, it's a neat problem. I really like this problem. So basically, let me show you the input. I always like to see what the input looks like. So our input is going to be 2 lines of text. There's the 2 lines there. And they encode a path that a line is going to take in 2-dimensional space. So each one represents like a path in 2-dimensional space. So when you start, they both start at the origin, and this one will go right by 1,007 units. Then it will go down by 949 units. Then it will go right by 640 units. Then it will go down by 225, etc., etc. So as you can see, this is describing 2 paths in 2-dimensional space. So let's go ahead and add the data to our collection of data files. And there we go. Oops. Oops. What are you doing? There we go. Okay. So now we should have text3 data, and we are ready to talk more about the problem. Okay. So here is a small version of these 2 paths. Obviously our input data is a lot bigger than this, but as you can see, this is the origin. One path goes right, then it goes up, then it goes left, and then it comes down. The second path goes up, it goes right, it goes down, and it goes left. Now, what they're asking us to do in the first problem is they want us to find all of the points where these 2 lines intersect, That's the sort of first part of the problem. And then the answer is, of these intersection points, find the one that has the closest Manhattan distance to the origin. If you guys aren't familiar with Manhattan distance, it's just the distance. So the Manhattan distance here, it's, I guess, only using horizontal and vertical lines. What is the distance to get between 2 points? So here you'd have to go over 1, 2, 3, and up 1, 2, 3. So the Manhattan distance here is 6. And it's, for anybody who, just think about the geometry for a second, right? It doesn't matter if we go up 1, right 1, up 1, right 1, up 1, right 1. Like, no matter what path you take, as long as you can only go horizontally or vertically, the distance between the origin and this point is always 6. So we need to find the intersection point that has the smallest Manhattan distance, and that is the answer that we output. So let's dig into problem 1, and I'll sort of explain how I solved it. Hopefully that's clear. All right. So, after already having solved the problem, I guess I'm going to explain. I don't know a good way to start, but let's explain it this way. We're going to keep some state as we loop over the input data. It's going to be a state, and it's actually going to have a hash map. So we need use standard collections hash map. And what this state is going to be, let's make it a type state. It's going to be a hash map where the keys are points, and the values are, I guess, initially just an array of 2 booleans, because we have 2 paths. And the reason why this is true, let's make a point. You guys know what a point looks like, right? Struct point has an x and a y coordinate. Let's make them I32s. And it needs to be hashable because we're putting it in a hash map, so let's derive all the things on our point. So points only hold numbers, so they can be copied, they can be cloned, we can debug them, we can do equality, and we can hash them. Partial eq. So now that we've derived all this business, we can put our points in the hash map here. So what we're going to do essentially is we're going to loop over the string of instructions, and for every point that we hit on our path, we are going to record whether or not we ever visited that point with this boolean. And there's going to be 2 of these booleans, because the first entry in this array will be if we ever hit the point on the first path, and the second entry will be if we ever hit the point on the second path. So once we have this sort of hash map of all the points that either line visited and whether or not they went through them, then all we have to do is filter out the points where both the first path and the second path visited that point, and those are our intersections. And then we just have to find the intersection among those that has the shortest Manhattan distance. So that's the strategy of this way to solve the problem. So let's go about doing it. So first of all, I guess we have to loop over our input just like we have been before. So let's if input.readLine at mute buffer ever equals 0, it means that we have run out of lines to process, so we break our loop. Sorry, this can fail. And just as before, we clear our buffer. I mean, this is kind of overkill. In fact, going back to the discussion of using iterators or not using iterators, let's just say for result in line dot lines, or sorry, for result in input dot lines let line equals result. So because we only have we know we're only going to have 2 lines of input. So, you know, avoiding deallocation is silly. So let's just use this because we haven't used it before. All right, so that's our line, and I mean, just to show you what we're doing, let's print this out. Guys, I'm sorry, I'm really sick today, so I'm going to be going slower, and this is a lot harder to do than the last time. Oops. Let's make this compile. Foo to string, foo to string. There we go. Print line. All right, so now at least we should be able to run cargo run day 3 with data03.text. And as you can see, indeed, all it did was print out the 2 lines. Wonderful. All right, so let's we're going to have to parse each of these instructions, is what I'm going to call them. So let's say we're going to get back a string in line.trim, to be safe, .split on commas, and just to be safe again, let's map that and trim it. So that's going to give us, you know, on the first iteration of the loop this, then this, etc., etc. Now we need to parse this into an instruction. So I sort of abstracted out the idea of an instruction. Let's say struct instruction has a direction, and it has a distance, which will make a usize, or actually let's use actual types, a u32, because it's always going to be positive. And a direction can be you know, up, down, right, left. Okay, so we need to parse each of these strings that we get back into an instruction. So let's do let instruction equals s.parse instruction, which can fail. Okay, good. So that's how we get each instruction out. But in order to be able to do that, we need to impl from stir standard stir from stir for instruction. And it's if you implement this trait, it will give you the ability to call parse on a string to get back that type. So if you're not familiar, this is a nice handy little trait in the standard library that is very useful, and we're going to implement it on instruction here. So in order to do that, we need to, this parsing can obviously fail, so we need to tell it, if we fail, what type of error do we have. This is an associated type on the trait. I won't sort of hesitate to explain whether or not I should explain what all these things are or just do them. I think I'll just do them, but if you don't know what an associated type is, it's going to be hard for you to follow. But anyway, and this needs to implement the from stir method, which takes in a string and outputs a result of ourself or the associated error type. So how do we parse this? Well, one thing I want to take advantage of here is we know that all of our input data is in ASCII, and so instead of dealing with stirs and strings and stuff like that, which would require extra allocation, let's just treat these like as bytes and ASCII characters. So what we want to do is we want to say, let's see, we want to say the bytes that we have, right, is s as bytes. And the first byte, should I do proper error handling? Let's not do proper error handling for a second, because we know the input is good. So let's say the first byte as a character is our character. So we pulled out the first character. And we need to that first character we need to interpret as a direction. So let's do, this is something I'll add later, but I'll show you again the try from, which is kind of neat. Let's do direction try from this. So we're going to try and parse this character into a direction, and that can fail. This method on direction does not exist yet, but we'll add it at some point. And then the rest of the string is, let's see, it's bytes from 1 to the end. And that we need to interpret as a number. And so there's a way to do this with a third-party library that does it like super efficiently. So let's go ahead and bring that in. Let's see, crates.io. What I'm looking for is the A2I crate, which basically just takes ASCII and turns it into integers. It's very handy and not in the standard library, but it's a great crate to use and a very basic sort of building block in Rust. So we'll put it into our dependencies in our cargo toml. Again, I usually don't worry about the minor version. I always leave it off. All right, so let's go back to day 3. So A2I, if we look at the documentation, has this function called A2I, and it is generic over the type of the type of integer that you want to get out, and it just takes a slice of bytes, and if it can parse it into an integer, it gives you some of whatever this generic type is, and if it can't, it gives you none. So this should be fairly easy to use. We want A2I. A2I is the crate. A2I is the function. The generic type parameter we want to parse this into is, what is it, a U32. We call that on our slice of bytes. And this returns an option. And we want to turn that option into a result, which you can do with OK, OK, or else. And this takes a closure. And now we can, this is basically saying if we get a none case, return an error. So we want to return the error, unable to parse into an instruction. And what we're not able to parse, we're not able to parse S. And so this whole thing, after we call OK or else, is going to be result, and we can propagate the error if we need to. And what this returns to us is the distance. And I need to quit and start again because RLS cannot figure out that we added a new library to our crate. But now that it can figure that out, it should no longer give us any problems with this. This is correct. Good. Now, the thing that we're missing is how to parse a character into our direction here. And so, I mean, notice, like, we could implement from stir on direction as well, but we don't have a stir, we have a character. And so something that was added fairly recently, actually, stabilized fairly recently to Rust, in fact, in the past year, is this trait called try from. And you say try from, well, in our case, we're going to try from a character, and we're going to implement this for direction. And this trait is extremely similar to from stir, except for it's generic. It's saying, like, I want to parse something into really anything. It doesn't have to be a string. Like, the from stir trait is basically that, right? But now with try from, you can sort of parse anything into your type. So this also, for the same reasons that from stir does, you need to give it an associated error that will be the result if we can't do the parsing. And then we need to implement try from which takes the type that we're trying to convert from and outputs a result of either ourselves, which in this case is direction, or the associated error type. And that's that. Now, try from is not in the standard namespace, so we need to import it. So now we have try from in scope. And we don't need to implement try from, we need to try from for direction. Good. Now all we have to do is, if we have a character, how do we make a direction? Well, we match on that character. If that character is u, then we want to return a direction u. And we want to do that for down, right, left, down, right, left. And if it's anything else, we want to bail with an error saying unable to parse character into a direction. And we give it C. Now this needs to return a result. So from this match statement, let's say this is our direction. And then let's return it. There we go. So now, if we get a character, we can easily turn it into a direction. So this is not a C anymore. This is a direction with this direction try from. Alrighty, so now we're ready to make an instruction out of the dir and the dist that we just parsed. Perfect. And in fact, let us, oh wait, what am I doing? Oh yeah, this is the instruction, and in from stir we want to return that. So let's just return it like this. There we go. So now, with all of that mess in place, we can just take a string and parse it into an instruction. Wonderful. All right, so we need to keep track of where we are at all times. So for each line, we first want to know where we start. And let's say we start at the origin. I'm going to make a little constant up here. So the origin is point of 0, 0. So we start at the origin. But then every time we get an instruction, we're going to move, right? Let's make a function called process instruction that will return us a new point, the new point where we end up. And this function is going to take the instruction. It also has to know where we are now, so it's going to take our point, it's going to take our instruction, and it is going to take a mutable reference to our state, because we also want to keep track of every time we go over a new point, we want to sort of record it in our state. I don't know if this can fail yet, but that will give us a new point. So we haven't written the process instruction point, but now we know where we are, and what we do is we just say, well, the point we're at now is now the new point. And we might have to add some more stuff later, but I think that's all we need at the moment. So let's write this function process instruction. It's going to take a point, which implements copy, so I mean, I don't have to worry about whether or not I take it as a reference or not. It doesn't really matter that much. It takes an instruction, which is an instruction, and it takes state, which is a mutable reference to our hash map. All right. Oh, and it returns where we end up. All right. So what we want to do in here, remember we want to throw into our hash map every single point that we visited, right? So we need to end up creating every single point we visit along this new line segment that we're creating while we're processing this instruction. So I guess the first thing is I want to match on the instruction direction. And let's see, direction U, direction down, direction right, direction left. And we're going to be moving. If we're going up, it means that we're not moving in the x direction, but we're moving up in the y direction. If we are moving down, it means we're not moving the x direction, we're going -1 in the y direction. If we are going right, it's this. And if we're going left, it's this. You'll sort of see where I'm going after I finish writing this. So we're gonna pull these things out and call them I and j. So what we're going to do now is we're going to say for every distance, for every number from 0 to all the way up to the instruction.distance, we're going to create a new point. And that new point is going to be, let's call this origin. So the point is going to be our origin dot 0 and our origin dot 1, but it's not going to be that because we're moving. But we only want to move by the right amount. I don't know how to explain this well, but what we want to move by is we want to move by I times, this needs to be, let's call this n. I times n here. And we want to move by j times n here. And this is interpreting the things as U32s because n is a U32, so let's make n an I32. All right. So let me see if I can explain this here. So with the picture. So we've got this instruction that tells us to move right? And we start out, this is our origin point. Well, actually, let's do a different line. Let's say we have an instruction to move up. So in the process function, we're going to be past this point, and the instruction, which encodes that first we have to go up, and then by how much we have to go up. So what we're doing in this for loop is we're constructing this point, and this point, and this point, and this point, and this point. Hopefully that's clear. And actually, we don't want to go. We want to go from 1 to all the way up to our instruction distance, because if n is 0, then we're just recording the same point that we started with, which will already be in our map. So we don't need to worry about that. All right, so we got this new point, and we want to add it to our state. So if you take state and call entry on it, explaining the entry API. I'll just write it out and then I'll try and explain it. Or insert with false, false. Let value equals. And then we want to say, something else we have to put into this process function. Okay, we have to know before we can do any of this stuff, whether or not we're the first line or the second line. This process instruction needs to know that. So let's call that the ID of the line, whether or not we're doing the first line or the second line. And let us, up here, initialize that to 0. And then once we finish processing a line, we will increment it by 1. So the first time we go through this loop, we're working on line ID 0, or path ID 0. And the second time we go through this loop, we're working on path ID 1. And then hopefully there are no more lines. So if we ever end up in the situation, we can assert, I mean, we don't have to do this, but we can assert that ID is always going to be below 2, right? It can be 0, it can be 1, but it should never be above 2, because we should never have input that's more than two lines or 2 paths. So now we are passing the idea of the path into this process instruction. Let's take that. ID is just a usize. So now we know which value to update. We update the value. So this value, I got to explain the entry API, but this value is an array of our 2 booleans, right? Or it's a mutable reference to that array of 2 booleans. Let me show you. So let's see, if we run this, it shows you, yeah, this is a mutable reference to the value in our hash map. And remember, the values in our hash map are arrays of booleans. So we want to say that the path, and this boolean, the first boolean is meant to track if we've hit this point with the first path. The second boolean is meant to track if we've hit this point with the second path. And so depending on which path we're using, we want to update that path's boolean value to true. Hopefully that makes sense. Let us, I can't borrow state as mutable. State needs to be mutable. Let's try and explain the entry API a little bit better by looking at the docs. So Rust deck. All right, let's look at hash map. And entry. Okay, so this gets the given keys. So you give it a key. So we gave it our point, right? And it gets the keys corresponding entry in the map for in-place manipulation. So what this thing returns is an entry. So when we call state.entryPoint, we get this entry type. And the entry is an enum that says either we're occupied, meaning we already have a key in our map that corresponds to the key we gave it, or it's vacant, meaning there was no key in there yet. But this or insert with is kind of the magic. So on an entry, we can call or insert with, and this returns a mutable reference to the value, but the value will always have something in it, because what or insert with does is it says, hey, even if I couldn't find a point in the map, if I couldn't find it, I'm going to put this value in the map at that point, and then I'm going to return you a mutable reference to it. So if this point already exists in our map, it'll just return the value that already exists. If it doesn't already exist in our map, then it will insert this as the value and return a mutable reference to it so that we can manipulate it. Hopefully that's clear. But that's the entry API. So we've got this instruction, which is essentially a line segment, right? And what we've done so far is we've gone over this line segment and we've entered into our map every single point that we hit along that line segment. And we've recorded whether or not we've hit it or not. So now what we need to do is return the new point that we end up at. And the new point we end up at is going to be this point on the last iteration of the loop. So let's initialize where we end up is our destination, let's say, and let's have that start out at our origin, and we will just update our destination every time we get a new point. And so by then, destination should be where we end up, and we can return destination. Why is that a result? Oh, because we don't return a result from this function. We always get a point. There's nothing that can fail in here. Perfect. So that's process instruction, right? So for every, we loop over the lines, and then we split them by comma, and then we parse an instruction out of that string. We parse an instruction out of that string, and then we do this process instruction, which essentially like records all the information we need in our state here, as well as returns us where we end up after doing that instruction. And then we set where we are currently to that new place, and as we go around again, all of this will just work. So I think this is enough to get us the answer to the first question. Let's see if that is correct. So we've been building up state in this map. And so now all we need to do is we need to take state and loop over the values. And we want to filter out any, we're not going to need the key, we're going to need the value. So if we don't have, if v0, the first Boolean, is false, well, what we want is for both v0 and v1 to be true. So we just need to say v0 and v1. We need both of these to be true, and that means that we found an intersection point, because it's a point that occurs in both paths. So after this, we'll have only the intersection points. And now all we need to do is find the smallest one in terms of Manhattan distance. So let's fold over this, and we'll start our state at none. And we will get, we'll keep updating the minimum, and this will give us the points. Well, this will give us the key and the value. So this is a point, and we're not going to need to use the value. And so in this fold function, let's see, all we need to do is calculate the Manhattan distance between our point and the origin, which will be some number. And if that number is less than, let's make this the minimum standard U size, or what are we using? U32 max. If our distance is less than the minimum, then we will set, we will set the minimum to this distance, and then the new state is minimum. So why is that not working? Because we need a comma there. And we need to say this fold is going to return us the answer. Good. So now what we need to do is encode Manhattan distance, which is super simple. So let's say Manhattan distance takes in 2 points, point A, point B, and it returns a U32. And all this is it's A's x-coordinate minus B's x-coordinate, absolute value of that, plus A's y-coordinate minus B's y-coordinate, absolute value of that. And I think this is gonna, all of these things are I32s, so we need to make this a U32. And I'm pretty sure that is correct. And this point, because we're iterating over with just iter, this point is a reference to a point, so we just need to reference it because it's copy, so we don't need to worry about that. And I think this is. Wait, why did I put this in process instruction? This does not need to be in process instruction. This needs to be up here. This is the answer once we're all done. Okay. So let's say that the first answer is formatting the answer as a string. All right, so let's run this and see if it gives us the right answer. 3 day or data 03. 4981, which is indeed the right answer. 4981. All right, so hopefully that was clear. As you can see, this problem is way more interesting than the first 2 days, and a little bit more involved. But it's sort of hopefully fairly clear what we're doing. Again, to recap, we start out with this hash map that's empty of points. And for each point, we're keeping track of whether or not we visited that point. And so we just loop over each path, and we record every single point in our hash map that we visited with sort of a Boolean that says we visited it. And then in the end, we just sort of loop over that hash map and only look at the points where we visited them both. And then we have all the intersection points. And here we just calculate which one of them has the minimum Manhattan distance, and that gives us our answer, and we're done. All right. So the second part throws in a little bit of a loop, and it says, look, find all the intersection points, but the answer is not the one that's closest in terms of Manhattan distance. The answer to part 2 is the one that's closest in terms of the total amount of steps that were taken across both paths to get to the point. So this example sort of does it well, right? The Manhattan distance to this point, I mean, this is clearly the closest of the 2 intersection points to the origin in terms of Manhattan distance, but it's not the closest of the 2 intersection points in terms of this new metric that we need to minimize, which is the total amount of steps taken. So as you can see, let's see, this is well, they have it here. So I think this is 8 steps over, 5 steps up, 5 steps left, and 2 steps down. So to get here, that path had to take 20 steps. And then the other one had to go 7 up, 6 across, 4 down, and 3 over to get to this one. So the total amount of steps across both paths is 20 plus 20 is 40. So this one takes 40 steps to get to. This one is shorter, however, because you just have to go 7 over, 6 up, and 2 across for 15, and then you have to go that's 7 up, 6 over, 2 down to get 15, and then this line goes 8 over, 5 up, and 2 over to get here, so that's 15. And so if you sum those together, it's 30. And so this intersection point is actually quote-unquote closer using the new metric of total number of steps taken. So hopefully that's clear. And luckily we can sort of use our solution from before, but we have to update it a little bit. So instead of keeping track of, for each point, instead of keeping track of whether or not we have actually hit that point, let us keep track of the total number of steps it took us to get to that point. Does this even need to be an option? I don't think it does. Let's say the total number of steps. So we're going to have an array of total number of steps. We're going to have an array of 2 values, which is the total number of steps taken. And so for every point, we're going to know that. We're going to keep track of it, et cetera, et cetera. And if we know that, then at the end, we can find the answer that sort of minimizes the sum of those 2. Oh, this still needs to be, I know why this needs to be an option. Because if we haven't visited the point at all, so we're going to have as a key, we're going to have an option U32 for path 1, and we're going to have an option U32 for path 2. And this is for every single point. So for every point, we'll have this, right? If the first path visited the point, then this will be sum of the number of steps it took for it to get there. If it didn't visit this point, this will be none. If the second path visited this point, it'll be sum of the number of paths it took to get there. If it didn't visit the point, this will be none. And we need to keep track of whether or not we visited at all, because of course down at the bottom, we only want to look at points where both paths have visited them. So we need to know that. All right. Hopefully that's clear. So what we want to do down here is we don't want to keep track. So these used to be Booleans, but now they are, we want to only look at paths where the first entry of this little array is sum, and the second entry of this little array is sum. So that fixes that. We also want to calculate, we can still calculate the minimum distance here in the same way we did, because we have access to the point, right? But now we also have access to the value, which is going to be the steps that number 1 took, and the steps, this is the, let's call it the steps array. This is going to be an array, right? So we know that the total steps of the 2 is, let's say, let's call this our array, just to make it easier. Our array is going to have a first element. We know that that is going to be sum because we filtered out the ones that are not sum, so we can unwrap here. And then we just add, and that's going to give us the number of steps that the first path took. The number of steps that the second path took is going to be this array 1.unwrap. And so this should now give us the total number of steps that it took to get to the point that we're looking at. And if that steps is less than the minimum steps, which is what we're going to be keeping track of here in a second, then we set the minimum steps equal to those steps. And at the end here, we need to return both the minimum distance and the minimum steps. So we're going to call this minimum distance now. Minimum distance. And our state here is going to be a tuple that starts out of standard U32 max for both. And this is no longer just one minimum, it's 2. So let's destructure that into mutable min distance and mutable min steps. And steps, min steps, steps. And that should then give us both answers, right? So this is answer 1 and answer 2. And so we return a string version of answer 1. And we return a string version of answer 2. Good. So that is this part of the code sort of updated. And hopefully you followed along, but basically our state contains every single point we've ever visited. We iterate over that. And then we filter out the ones where that are not intersection points, because either the first path didn't visit it and so its value is none, or the second path didn't visit it and its value is none. And then we try and find the minimum Manhattan distance and the minimum number of steps by folding. And our initial state, so the minimums initially, we're going to initialize to just a huge, large number. And then this closure is going to be run every time we iterate. Every time we iterate. So remember, with fold, you pass in a closure that represents the current state. So we get in the current minimum distance and the current minimum steps. And it also gets as a parameter the key and value of the map that we're iterating over. So we get a point, and we also get the array, which is that value of optional U32s. The distance of this particular point to the origin is the Manhattan distance here, and if that is less than what our current state's minimum distance is, then we set our minimum distance to that, and then the number of steps it takes to get to this point, right, is just the number of steps that it took the first path to get there plus the number of steps it took the second path to get there. And then again, we sort of compare that to the running minimum that we've been keeping, and if it's lower, then we set the running minimum to that, and then sort of we return our new state. And by the end of all of this, what this gives us is the 2 answers. So we still have some issues because this is all messed up. So here we're not going to insert into our map 2 booleans, we're going to insert none and none, right? And so when we get a mutable reference to the value, we cannot do this. What we need to do is we need to say, so we always want to keep track of, this is also in the problem. So you can imagine on these paths, like the path is going along and it hits a point, and then it goes somewhere else, and then it comes back and it hits that same point again, right? Well, for our purposes, we're only concerned with the first time it hits the point. So we want to make sure that the distance, the number of steps that it took to get to that point that we're recording is the first one, not any others. So we're only interested in updating this value if the value is none, right? Or if the first value, if the value for the path we're taking is none, that's the only time we want to update it. If we find a value here that's some, it means that we've already visited this before and recorded the number of steps, and that's necessarily going to be smaller than the number of steps we've taken so far. But if this is the first time we're seeing the point, so this is basically saying if this is the first time this path has seen the point, right, then we want to update the value for that path to be some the number of steps we've taken up until now. And I think that does it. But the problem is we don't know, because we haven't been keeping track of the number of steps that we've taken up until this point. So we're going to have to keep track of that and pass it in here. So the total number of steps we've taken up to this point is 32. So we need to know that. So in process instruction up here, we need to know how many steps we've taken up to this point. And we need to keep track of that. So we need to do it, we don't do it up here because this is for both lines. We need to do it for each line. So just like we're keeping track of where we are for each line, we need to keep track of the number of steps for each line. We start out at 0. And then after every instruction, let's see. Oh. So this is wrong down here. So what we want to pass in here is the number of steps that we've done so far, not including this new instruction that we have. So down here, we want to definitely say, once we've reached a point, we want to record the number of steps we've taken, but it's not this steps, it's also plus the distance that we've gone to get to the point that we're talking about now, which is in. Yes. Okay. All right. So we want to pass into this function the number of steps we've taken before we did the instruction. But then after we do that, we want to update the number of steps by however long the instruction told us to go. And instruction is moved. Well, instruction should be copy. Where's instruction? This should be copy. Derive, copy, clone, debug, all the things, which means this needs to be copy. And now we don't, since it's a copy type, I mean, it's just holding numbers essentially, so we don't need to worry about ownership with this type. And that way we don't have to worry about it having moved, because, well, if you guys aren't familiar with Rust, right, like, so if we have this instruction type and then we pass it into a function, normally that function, that like variable is completely moved into this function and will get destroyed when this function exits. But for copy types, which are only like small things like numbers or things on your own types that you say should be copy, like this will not move instruction into the function. This will just make a copy of instruction and give that to the function. And so instruction will still be alive after, like down here. So hopefully that was helpful and useful and makes sense. So I think this might work. Let's check it out and see if we have any problems. It seems to have worked, and we got 16412, which sounds like the right answer. 16412. It is indeed the right answer. And so there we go. We've solved part 1 and part 2 of day 3. And hopefully you guys were able to follow along and sort of get that. But as you noticed, it took a while to run, right? It took, in fact, if it's anything like the other implementation I had, oh, I don't want day 3, I want this. It took on the order of milliseconds, between 58 and 90, or 58 and 59, which is good, but it works. At least it works. So that is, let's go to our to-do. I'm lost. So that's day 3 done. Maybe we need to put tests in. Let's put tests in, because we're supposed to put tests in everything. I told you this one might go long, but this is a cool problem, and so I'm not worried about time. So let's add tests, and on admin of code, we have a couple tests here. If we're given this input, let's see, let test cases equals so that's one input, and the answer we're supposed to get out of there is 159. And this input should give us 135. And actually, I need to be careful here. This is a new line. Oops. And this is also a new line right here. Oh, and these need to be tuples. There we go. And this is input expected 1 for the moment. And expected 2 for these is 610 and 410. 610 and 410. 610 and 410. So this is input, expected 1, expected 2. And I suppose we can put in the original case. So that is, where's this? This is here. Yeah. So the first wire in the simplest case is this, and the second wire is this. And for that one, we should get, I think it's 6 is the Manhattan distance. Yep, 6. And for this one, we should get 30 steps, right? All right. So there, we have our 3 test cases. So for input, expected 1, expected 2 in test cases. Test cases let us run. Let us create a reader, which is an IO buff reader new of input as bytes, and let us run reader unwrap, and that gives us answer 1, or well, actual 1 and actual 2. What use of undeclared module I? Oh, we don't have use super. Use super star. Okay, and now we need just to assert that actual 1 is equal to expected 1, and we need to assert that actual 2 is equal to expected 2. And we can't compare a string with a stir, so can we do that? There we go. Let's see if this works. Cargo test. It's got to compile criterion because we put it in our deb dependencies. So let's take a second. And that passes. So that is day 3 really done. Where is my to-do list? So that's day 3 really, really done. But I want to talk to you about something that, at least for this input, is a hell of a lot faster. I'm not sure if it scales better or not. That's an interesting question, and all of you computer science people with your O of n's and O of n squareds can worry about that. I know a little bit about that, but I haven't really sort of analyzed those things in depth. But at least the first version I tried, which is not this, runs a hell of a lot faster than this. And I think the reason is, the reason why this is slow, I would guess, is because we have this hash map which like gets huge, right? In fact, we could sort of mitigate that by not worrying about memory and just initialize a huge hash map to begin with and see if that makes it run any better. Oops, times. But I don't think it's going to run that much faster. I think there's just cargo run. Let's see, 3 data 03. It's still going to take a while. Yeah, it's still. I mean, you saw the pause there. It still takes a while. So I don't know what about this makes it a lot slower than the last version, but I think it has to do with we're keeping track of every single point, and we're doing a lot of inserts and lookups in this hash table, which has just a ton of points in it, like a really, really large number of points for like a few number of intersections. Like I think I was looking at this data, there's like 300 intersections in total, but the number of points, well, I guess we can just look at the number of points. So how many points do we end up seeing at the end of this? Print line, oops, state.len. So let's run this and see how many points we ended up looking at in total. We ended up looking at a lot of points, 297,000 points, which is crazy. And so we have to insert those into the hash map, and we have to look up those points and mutate the hash map for every single one of those points. And so maybe that's why it's taking so long. But my day 3 solution, the second version of my day 3 solution, and here let's do a split screen. Let's open this up twice because I want to navigate around this file. So here's the much faster version, which takes a totally different tact or approach. And what it does is it basically says, as we're looping through the data, let's not keep track of points. Let's keep track of entire line segments. So we loop through the data and we get a path for the first path that is composed of a vector of line segments. And then we get a path for the second path that's composed of a vector of line segments. And then line segments know how to tell if they intersect with another line segment. So you take so it's O n squared over the number of line segments, because you have to sort of loop over every line segment in path 1 and every line segment in path 2, and you ask them to compare them. Sorry, to compare themselves and say, hey, do we have a point of intersection? And that's how, in this sort of method, you get the intersections. And then once you have all the intersections, then at the end you sort of loop over those and you calculate, the one with the minimum Manhattan distance in the case of the problem 1, and you calculate the one with the minimum total number of steps in the case of 2. Now this is a pain. I didn't want to code this live because it's a pain to sort of work with these line segments, at least the way I wrote it. So I don't know if you guys have any suggestions to make this code cleaner. Let me know. But let's just run through this code. So the first thing we do is call this parse input function, and we give it our reader. So this parse input function, similar to before, we're doing the similar loop over every line, right? So we got our buffer where we're going to read each line into. We keep track of, I think I called this pass as ID. I called this ID in the other one. We keep track of which line segment we're doing. Let's make this, there we go. We keep track of which line segment we're doing. I guess I better not, since I have 2 buffers open, I guess I better not make any, I better figure out which one is the one that I'm going to make changes to, because I can't I don't think with Vim I can modify both files at the same time. Let's make this bigger, there we go. So anyway, we're here in the function, or we're here in our run function, and this calls parse input, which is here. So we loop, we read each line. If our input has more than 2 lines, we bail because we can't handle that. We keep track of our point just like we did before. So initially this is set to 0. We keep track of our number of steps that we did before, so this is initially set to 0. And then here's where we sort of loop over every single instruction. So in here we're dealing with instructions. We parse out that instruction, which is I didn't use the try from and stuff like that in this code, but you can see we're just looking at the instructions as bytes. We're pulling out the first character. We're turning that into a direction like we did before. Then the remainder of it we're parsing into a number, which is the distance, and then we're saying that's our instruction is the distance and the direction. And then we take our point and we take the point we're at now, and we add the instruction to it. So this allows me to show off something kind of interesting about, so how do we add, how do I take a point and add an instruction? Well, we have, just like we had before, let's see, we have our point struct, which is just a point, and we also have an instruction struct, right? But we want to take an instruction and be able to add it to a point. So to do that in Rust, you just implement add, right? And I'll explain what add is. So you implement add, and this is the right-hand side of the add. This is the left-hand side of the add. And you tell it what you're going to output. So if we have a point and then we add an instruction, I want to know what is the new point that we got to. So our output type is going to be a point. And then you just implement this add function, which gives you the right-hand side, and it gives you the left-hand side. So we match on our instruction. If we go up, the new point we're going to go to, right, is the same. Its x value is the same as it was before, but the y value has gone up by the distance of the instruction. If we go down, same thing, except for the y value has gone down by the distance of the instruction. If we go left, we subtract the distance from the x value. So you get the point. This is how we can sort of take a point and add an instruction and get back a new point, which is what we're doing here. So our new point, our destination, is there. And then we have this business of, like I said, we're accumulating line segments. So in order to create a line segment, the things we need to know, well, the line segment needs to know how many steps it took to get here. And it needs to know its origin point, and it needs to know its destination point. So once we have that, we can create a line segment, which is a type I'll show you below, and we have this segment. After that, we increment the number of steps that we're accumulating. We set our new point of origin to where we ended up after applying the instruction, and we're keeping track of all these segments. So we have this paths variable, which is just an array of two paths, right? And a path is just a wrapper type around a vector of segments. So think of this as a vector of segments. I'll show you that in a second. But here we'll be accumulating all of the segments that we did on path 1, and here we'll be accumulating all the segments we did on path 2. So depending on which ID we're working on, we just push each segment we newly create to this sort of collection of segments that we're keeping. Let's not write to it. I don't want to mess this up. Okay, so that should be clear. And then at the end of this function, what we get out, right, is this array of collections of line segments that we've been keeping track of for both paths. So let me show you the path. The path type is just a wrapper type over a vector of segments. Yeah. All right. So that gets us. That's parsing our input, and it gets us these two paths, which are vectors of line segments. And then to look for intersections, right? Like I said before, we loop over all the line segments we have in the first collection of paths. We loop over all the line segments we have in the second collection of paths. And then we say, hey, segment 0, do you intersect yourself with segment 1? If so, tell me the point at which you intersect. And if we get one of those, we push it onto a collection of intersections that we are keeping track of. If we end up with no intersections, then that's bad. It means we couldn't find any, so we just bail. And then here is, like before, how we sort of calculate the minimum. So now that we have all the intersections, we just initialize minimum distance and minimum steps to some really large value. And for every intersection, we get out the point and the number of steps that it took to get there. And then we calculate the Manhattan distance from this point to the origin. If that is lower than our minimum, then that's our new minimum. And then if the number of steps it took to get there, the total number of steps across both paths is less than the minimum we're keeping track of, then that's our new minimum. And then the answer is just, that's the answer. So the hard part, and the reason why I didn't want to code this live, is this function here to have a line segment and figure out whether or not it intersects with another line segment. That ended up being hairier than I wanted it to be. But if we come down here and we look at segments, you can see what a segment is comprised of. So a line segment just has the origin point, the destination point, and the total number of steps that we've taken up until now. And that is a line segment. I also have this notion of a segment kind, so I want to know whether or not our line segment is a horizontal line, in which case I'm keeping track of the range of x values it goes over, and if it's horizontal, it'll just have one y value. If it's a vertical line segment, it'll just have one x value, and it'll have a range of y values that it goes over. So I guess we should look at that. This segment knows how to give you its segment kind down here. So if you call the kind method on a segment, it will return you what kind of segment it is. And you can see that if both the x values, or sorry, if the origin point's x value and the destination point's x value is the same, that means we have a vertical segment. We sort of calculate here what it is. Otherwise, if both y values are the same, we know we have a horizontal segment. And then this is unreachable because I am not allowing you to create in the constructor for a line segment. I'm not allowing you to create a line segment which is neither horizontal nor vertical. So the reason why I can call unreachable there and know that we're not going to panic is because I have this, I return an error if we ever try and create a line segment that is not horizontal or vertical. Anyway, okay, so this line segment knows how to calculate, in addition to its kind, it knows how to calculate the number of steps in total that it takes to get to a particular point. And that is, so remember, we're keeping track of, in this line segment, this is the cumulative number of steps we've taken up until we do the instruction. So we have this cumulative number of steps we've ever taken, plus the new steps that it would take to get to this particular point, which is just the Manhattan distance between the origin of our line segment and whatever this new point is. So you can see this is sort of saying, this is saying what's the cumulative number of steps it would take you to get to a particular point. And then we have this fun intersection function, which is, I was telling you I didn't want to code live, right? But we have a line segment, and we have another line segment, and we want to ask them, hey, do you guys have an intersection point? If you do, return it to me. If you don't, give me none. So first we figure out, is the first line segment horizontal? Great. Then we figure out, is the second line segment vertical? If it's not, we don't have an intersection point, because we're not going to deal with intersections of horizontal lines with horizontal lines. And same thing here. If the first one is vertical and the second one is not horizontal, then we don't have an intersection. So vertical lines do not intersect with vertical lines, and horizontal lines do not intersect with horizontal lines, at least in my in this code, because you can imagine a problem where that mattered, but it doesn't matter in this problem. Okay, so we've got so if we have a horizontal, we just pull out the x and y the x and y values for that horizontal line, and we get the corresponding x and y values for the other vertical line, and then we do this business to figure out if they intersect, right? So let's see, if you're dealing with a horizontal line, this is a range, right? Well, this is two numbers. It tells you where you started in x, where you ended in x. This is just one number. So we say, look, if the range of where we started in x to where we ended in x contains the x value of the other vector, the vertical one, then we need to worry about continuing. And then in order for this line to intersect, you have to check that again for the other line. And if you do all that, then you know the point of intersection. By the way, I don't know if I coded this in the other one, but if the intersection point is the origin, they don't want you to count it. So anyway, then we have the point of intersection. And remember, this segment is keeping track of the cumulative number of steps it's taken up until now before we apply the instruction. And this steps to is going to, if we give it the point of intersection, it's going to give us the total amount of cumulative steps it takes to get in addition up until that point. And we need to know what those values are for both the first sort of path and the second path. And so this is the sort of total cumulative steps that it takes you to get to the intersection, and then we return that. And an intersection is composed of, again, what point the intersection is at and the total cumulative steps across both paths that it takes to get there. And sort of once you do all this business, that makes sense. So let us quit out of this. Oops, I want to quit without writing. And wire this up, and we'll see like how much faster this is. So we want in our lib to have a new mod that is day3 v2. And in our main function, instead of running day3 as a run function, we want to run day2 or day3 version 2's run function. But day3 version 2's run function needs to have its signature updated for the updates we did before. So this now needs to return a tuple of strings, right? And which means down here we need to return, let me pull this from here. So we need to return this. And we need to no longer print. And the answers are, in this case, the minimum distance and the minimum steps. And so now day3 version 2 should have the same signature as all our other run functions, and this should no longer give us an error. Oh, I can't find it. Why can't you find? Can you find it now? Day3 version 2 run cannot resolve cargo check. Cannot resolve day3 version 2 in AOC. So that means we messed up in our library. Day3 version 2. We totally have that module. It's got a run function with the right signature. Oh, good. Now we have a different error. It was something with, I didn't save the files. So day3 version 2 85. We renamed this to ID. So we renamed it to ID, cargo check. Now let's try cargo run day3 with data 03. And that is almost instantaneous, much faster. So let's add a benchmark to see how much faster we go here. So we want to run day3 v2 in our benchmark. That works. So let's do cargo bench. See what it gives us. Oh, in cargo bench, you can just run one benchmark if you do this. Target 03. So we don't have to run day 1 and day 2 again. That did not work. Oh, because you give it what you call it. So we're calling it day 03 v2. There we go. And as you can see, this version takes about 600 microseconds, whereas the other one was taking about, what was it, about 60 milliseconds. So if we go back to our benchmarks, our report, if we reload this, and we now look at day 3 v2, this is a much, let's bring this and this up on the same screen. How do I make you come out into your own separate window? Oh well. Oh, you are in your separate window there. Okay, good. And then you need to go back to here. And as you can see, day 3, whereas when I benchmarked it before, it takes like 3 minutes to benchmark this, which is why I'm not going to do it again. But we were taking roughly 60 milliseconds, and now we're taking 650 microseconds. So for whatever reason, the first version I sort of built that dealt with line segments goes a hell of a lot faster. I think we might be done for the day. Let's commit everything to GitHub. So let's run git status. What did we do? So we added benchmarks. We added the day 3 data. We changed day 3. We changed day 3 version 2, and we changed lib and main. So let's git diff and see if this is what we want. So we added the ATI package, that's correct, and we added criterion, so we added a whole bunch of stuff in our cargo.toml. That's all right, that's all right. Let's get to the bottom. Criterion brings in a whole bunch of packages. Okay, we changed our cargo.toml to bring in ATI and criterion. In day 3, it's almost a brand new file, right? And the second version, just at the end there, we modified the, made it return a tuple of strings like all the other run functions. And we changed ID because that's more intuitive to me. And then in our main function, or in our lib function, we just added that new module. And our main function, day 3, is now using the faster version. So that all looks good, except for the one thing I'm remembering that we have not done is add tests to day 3 version 2. I think we can just copy what we have here over to day 3 version 2, and we should be good. Source day 3 version 2, add those tests down there. And let's see if we run cargo test. Yeah, good. It tests day 3 and it tests day 3 v2 and everything passes. So with that little addition, I think we are all good and I'm ready to push this to GitHub. So git status, git add all, git commit im. Day 3. Git push. Alright, so you can be closed. Did I close GitHub? I did. So now we have day 3. Day 3 version 2 and day 3 version 1. Maybe I shouldn't call them that because, like I said, I did this one first. But the one I actually coded for you guys live was this one. So I don't know. But there we go. All right. Well, if you have any comments or suggestions on these videos or how I'm doing or sort of observations, again, please feel free to leave a comment or even email me. I think you can find my email through GitHub somehow. But leave a comment on the YouTube video or leave a comment on I guess I'll post this again to the Rust Reddit, although that hasn't been getting a lot of attention, so maybe I'll stop doing that. But for this one, I'll post the Rust Reddit again, so you can leave me a comment there. Otherwise, this has been super fun. I don't know if I'm going to have the time to continue at this pace for the remaining of advents of codes. Today was like particularly time intensive, and so I don't know. We may have to switch from doing advent of code to like doing less frequent but sort of more realistic live coding, where I actually, instead of doing advent of code problems, I like work on an open source project, or show you a couple libraries that I've written. So I might switch up. I might continue with advent of code. I'm not sure, but we'll see. So with that, I'll sign off, and until next time, thanks.